This video discusses describing functions of standard nonlinearities. The concept of describing function was detailed in the previous videos. Here we consider an on-off relay. The transfer characteristics of an on-off relay is shown in the figure. It shows that the output switches between plus m and minus m for any input. Let us assume that the input is given by x equal to capital X sin omega t. Y is equal to capital M in the interval 0 less than omega t less than pi, and y is equal to minus m in the interval pi less than omega t less than or equal to 2 pi. The above output seems to be odd symmetric, that is, x of minus t is equal to minus x of t. Hence, cosine components will be totally absent in the Fourier series expansion. By the Fourier series expansion, the output y can be written as a1 cos omega t plus b1 sin omega t. The average component and higher harmonics are neglected because the describing function is a harmonic linearization approach. Also, since the output is odd symmetric with respect to the y-axis, the cosine component is absent. Hence, y can be reduced to b1 sin omega t. We can easily find the coefficient of b1 by using the equation 2 by t integral 0 to t y sin omega t d omega t. Since b1 is the coefficient of the sine function, here we use sin omega t. And the period of the signal can be considered to be 2 pi. Hence, b1 can be reduced to 2 by 2 pi integral 0 to pi m sin omega t plus integral pi to 2 pi minus m sin omega t d omega t, that is equal to 4m by pi. Hence, y is equal to 4m by pi sin omega t. Hence, if you consider an on-off relay, if capital X sin omega t is the input, the output would be 4m by pi sin omega t. Describing function is the ratio of the amplitudes of the fundamental component of frequency to the input magnitude. Hence, Kn of x can be written as 4m by pi x angle 0. Here we can see that there is no phase shift between the input and the output. The output starts exactly when the input starts and completes its one cycle at the same instant when the input completes its one cycle. Hence, Kn of x is equal to 4m by pi x angle 0. That is, describing function of an on-off relay is 4m by pi x angle 0. Here we look at the describing function of an on-off nonlinearity with dead zone. The figure shows a dead zone in the range minus delta to plus delta. It shows that the output will be 0 till the input magnitude reaches capital delta in the positive half cycle. And when the input magnitude is greater than delta, the output will be switched to a constant value, which is positive. Similarly, in the negative side also, when the input is less than minus delta, the output switches to minus negative value, else the output is 0. Hence, we can see that the output will be a square wave as shown in the figure. Hence, in the output, the switching takes place at omega t is equal to alpha. This corresponds to x is equal to delta. Hence, we can write delta equal to capital X sin alpha or alpha equal to sin inverse delta by x. One can easily verify the instances of pi minus alpha, pi plus alpha and 2 pi minus alpha where the output switches from one state to another. By applying the harmonic linearization approach, y can be written as a1 cos omega t plus b1 sin omega t. And since it is odd symmetric, cosine components will be absent and y can be written as b1 sin omega t. If you look at the waveform, the entire period can be easily divided into 4 regions, and hence integral 0 to t can be written as 4 times integral 0 to t by 4 because of the symmetry of the wave. Hence b1 is equal to 2 by 2 pi, which is the period, 4 times integral pi by 2 y sin omega t d omega t, that is equal to 4 by pi integral alpha to pi by 2 because it starts only at alpha, capital M sin omega t d omega t. This results in 4m by pi cos alpha. Hence we can write y is equal to 4m by pi cos alpha sin omega t. In this case, 4m by pi cos alpha is the maximum value of the fundamental component of the output signal. For a given waveform and for a given dead zone, alpha will be a constant. Hence, 4m by pi cos alpha is a constant value. If the input to this nonlinearity is capital X sin omega t, output can be written as 4m by pi cos alpha sin omega t. The ratios to be compared will be x and 4m by pi cos alpha. Thus, describing function is 4m by pi cos alpha by capital X. Since alpha is a term which is introduced by the user, we can write it in terms of the dead zone parameters, that is equal to 4m by pi into root of 1 minus delta square by x square by x. We have seen that sin alpha is delta by x. If you look at the input and the output, there is no phase shift between the two signals. Hence, describing function is equal to 4m by pi root of 1 minus delta square by x square by x angle 0. This shows that y is a function of x. Here we discuss the describing function of a dead zone nonlinearity. The transfer characteristics of a dead zone nonlinearity is shown in the figure. This shows a dead zone in the region minus delta to plus delta. We can see that once the amplitude of the input exceeds delta, the output starts from 0 with a slope of 1. At the output, we get a waveform starting from 0 and has a shape exactly as that of the input. It is clear from the shaded region. Hence, the magnitude of the output at any instant beyond alpha would be x sin omega t minus delta. That is, at every instant of time beyond alpha, the magnitude would be delta less than x sin omega t, where x sin omega t is the input signal. With this idea, we can write y using these equations. Applying Fourier series representation, y is equal to a1 cos omega t plus b1 sin omega t. The odd symmetry of the wave gives 0 values for the cosine components. Thus, y is equal to b1 sin omega t. b1 can be found using the same rule as applied to the previous case. Integral 0 to t can be written as 4 times integral 0 to t by 4 due to the symmetry of the wave. Hence, we can write b1 as 2 by 2 pi 4 times integral alpha to pi by 2 because it exists only from alpha x sin omega t minus delta magnitude of y sin omega t d omega t. Since delta is equal to capital X sin alpha, cos alpha and sin 2 alpha can be written as delta by x root of 1 minus delta square by x square and 2 delta by x into root of 1 minus delta square by x square respectively. Finally, we get the result of b1 like this. Here, the input and output of the nonlinearity can be represented as x sin omega t and B1 sin omega t. It shows there is no phase difference between the input and the output. Hence, the describing function Kn of x will be capital B1 by capital X, angle 0. Thank you.